It's my pleasure now to introduce Scott Moreland, who is at Duke University working in nuclear theory. His advisor, Stefan Bass, is here today. Again, like everyone that I'm introducing, he did his practicum at Lawrence Livermore. I feel like I need to take a ribbing on that one, in 2014. And his presentation title today will be Determining QGP Initial Conditions. I hope it's the same title. Quark-Gluon plasma initial conditions and transport properties with quantitative uncertainty. So Scott, it's your show.
Right, so I'm going to talk about determining quark-gluon plasma initial conditions and transport properties with quantitative uncertainty. This is work that I conducted under the guidance of Stefan Bass, who is in the audience. We know that protons and neutrons have substructure, namely that they're composed of constituent quarks, C-quarks, and gluons. And an important question to ask in high-energy nuclear theory is, when are these degrees of freedom liberated? You can perform a very crude back-of-the-envelope estimate and ask yourself when the energy density of nuclear matter would exceed the rest mass of the proton. And if you basically approximate the system as a massless gas of gluons, you arrive at a temperature of about 200 MeV. And so this tells us that it's possible that the proton may melt at a temperature of about 2 trillion Kelvin. More rigorous QCD calculations show that the phase transition occurs at about 155 MeV, at which point the nucleons melt into a deconfined soup of quarks and gluons, which is dubbed the quark-gluon plasma. And one of the fundamental goals in high-energy nuclear theory is to map out the phase diagram of high-temperature and high-density nuclear matter, in particular to find the transition from a hadron resonance gas to a quark-gluon plasma. The quark-gluon plasma is believed to exist or to have occurred naturally in two places in nature. In the very early universe, mere microseconds after the Big Bang, temperatures were much hotter than they are today. And also, it's believed to exist at the center of neutron stars at very high baryon density. In order to study the quark-gluon plasma experimentally, the general strategy is to collide nuclei at ultra-relativistic energies. This is done principally at two locations, at the relativistic heavy ion collider, which has beam energies ranging from about 10 GeV to 200 GeV per nucleon pair in the center of mass frame, and also at the Large Hadron Collider, which has energies from about 2.76 to 13 TeV per nucleon pair. And so the way this works is you boost two nuclei close to the speed of light. They become Lorentz contracted along the direction of motion and appear pancake-shaped in the lab frame. The nuclei collide, compress and heat matter beyond the QGP critical point at sufficiently high beam energy. The QGP rapidly thermalizes and begins to expand hydrodynamically. And then the liberated quarks and gluons eventually must recombine into colorless hadrons, which free stream before they hit the detector. So the types of questions that we want to ask about quark-gluon plasma are very similar to the types of questions that we'd ask about more ordinary matter, such as water. So we want to know, what is its equation of state? So for example, what is the relationship between pressure and energy density? We want to know how and under what conditions it's formed in a nuclear collision. We want to know its transport properties. So for example, the QGP shear viscosity and its bulk viscosity as a function of temperature. We'd like to know how an energetic probe loses energy as it traverses a QGP medium. And also, we'd like to know how it recombines and forms colorless hadrons. So the difficulty in studying the QGP experimentally is that the kinds of questions that we're interested in are intrinsic properties of the QGP medium, its equation of state, the transition temperature, its viscosity. But the QGP that is produced in a heavy ion collision only has about 10 to the negative 14 meters spatial extent and only lives for about 10 to the negative 23 seconds. So what the experiment sees is only the very late time final state observables. So we can only measure for example, the particle yields, the average particle momenta, and angular particle correlations, which I'll talk about momentarily, of the final state hadrons. So one notable example of using final state particle information to reverse engineer the collision and infer properties of the initial QGP medium is something that is done to study the QGP viscosity. When you have a heavy ion collision, your two nuclei typically collide at some random offset, known as the impact parameter. And the region of overlap forms this Venn diagram-shaped, almond-shaped region in the upper right-hand corner. And because of this elliptic almond shape, you have pressure gradients which are steeper along one dimension of the ellipse and longer along the other dimension of the ellipse. And this means that the hydrodynamic expansion is more vigorous along the short dimension of the ellipse. And so you actually measure more particles that come out along the short axis of the ellipse. And so this quantity, which measures this anisotropy, is known as the elliptic flow, represented by this V2 symbol. So it's mathematically, it's quantified by the second Fourier coefficient of the angular distribution. And the way this works is you have a simulation which you believe recreates the collision. You run your simulation with different values of the QGP shear viscosity. And it turns out that by increasing the QGP shear viscosity, you decrease or dampen the amount of final state elliptic anisotropy. And so you can see in this figure on the right here that they have different theory calculations, these colored curves, for different values of the QGP shear viscosity divided by S is the entropy density. And then they have this data from Phobos at RIC. And what was found that was really surprising is that the QGP has a very small specific shear viscosity. In fact, it's so much smaller than other systems in nature that it was postulated that the QGP is the most ideal fluid in nature. So in order to do this process and to extract intrinsic properties of the QGP medium, we need a transport model to connect experiment and theory. And so the current transport model that's typically used is referred to as the hydrodynamic standard model. You first determine the initial energy density or entropy density that is produced in the overlap region of the collision. You then evolve this through relativistic viscous hydrodynamics, which imposes energy and momentum conservation. And the hydrodynamics code requires input for the QGP viscosity parameters and also for the equation of state, which is determined by Lattice QCD simulations. And then finally, at some point, you have to particleize or hadronize your QGP medium, and then you continue to evolve the system using a Boltzmann equation where your hadrons rescatter and then ultimately free stream, at which point you can compare that final state data to something that you'd have in an experiment. So the process of running a model with under-constrained model parameters, matching your model to experimental data, and then tuning your model to fit that data and extracting out the best fit or optimal values of the model parameters is a process known as model-to-data comparison. And so really what you're trying to do is solve an inverse problem where you have some model with some unknowns, and you want to optimize those unknowns to fit some observed data set. And from this process, then, you can extract new physics insight about intrinsic medium parameters that you cannot directly access experimentally. So now I want to move on and talk about my own work and my own contributions. And an important question to always ask is, what are you doing and why are you doing it? And so I want to talk specifically about 3 projects. The first is my practicum, which I did at Lawrence Livermore National Lab. And for this project, we looked at the Lattice QCD equation of state calculations, which are input for the hydrodynamic simulations. And what's really nice is that you can actually calculate the QCD equation of state directly from the QCD Lagrangian. You can express the vacuum-to-vacuum transition amplitude in the Feynman path integral formalism. And then if you make a substitution where you replace time with imaginary time, that amplitude resembles the form of a partition function. And you can then discretize the partition function on a lattice and determine the QCD equation of state. So that equation of state, for example, would be pressure as a function of energy density or as a function of temperature. And so what we wanted to do is that there are multiple calculations that perform to determine the QCD equation of state. And we wanted to check to see to what extent do differences in the calculation, which are mainly numerical differences, to what extent those actually affect the predictions for experimental observables once those calculations are embedded in hydrodynamic simulations. And so we took 3 different state-of-the-art Lattice QCD calculations. We embedded it into a modern Monte Carlo simulation for relativistic heavy ion collisions. And we performed this calculation on the Open Science Grid. So it was a large-scale calculation, many terabytes of data. And so these are the 3 different equations of state here. And then we were able to calculate the effect on different experimental observables. And long story short, what we found is that between the 2 state-of-the-art Lattice QCD calculations, that the effect on observables were very small and things that you would not be able to detect with current experimental uncertainties. So this is nice because it tells you that current Lattice QCD calculations are in good shape and don't necessarily require large future improvements for relativistic heavy ion collisions. Next, I want to talk about improving theoretical descriptions of the QGP initial conditions. So what are the QGP initial conditions? So the initial conditions are the energy density and fluid velocity at some time at which you start the hydrodynamic simulation. So in principle, this is some 3D field for the energy density. Although in reality, in modeling, it's common to project out this eta coordinate, which is related to the beam dimension, and look at these initial conditions as if you were looking down the beam pipe. And in that scenario, they become 2D initial conditions. And actually, I have a model here that I brought that if you could just pass it around, people can look at it while I talk about this. There is a problem with the QGP initial conditions. It's that they're not very well understood theoretically. There are many models and theories proposed in the literature. Just some of the names are listed over here. And the QGP viscosity is extracted by tuning the simulation viscosity to fit this elliptic flow data. And the problem is that different initial condition models predict different flow behavior and hence prefer different QGP viscosity values. And so what this means is that the extracted QGP viscosity depends on the theoretical initial conditions, and thus estimates of the QGP viscosity inherit the large theoretical uncertainty in the QGP initial conditions. And the solution that we came up with to this problem to circumvent this issue is to apply a data-driven approach. So we parameterize the QGP initial conditions using a flexible meta-model, and then we apply rigorous statistical methods to simultaneously constrain the QGP initial condition and medium parameters. So the model that we came up with is called TRENTo. It stands for Thickness Reduced Event by Event Nuclear Topology. We were also in Trento, Italy when we came up with the model. So it's actually quite easy to explain. First, you sample the positions of nucleons within your colliding nuclei. Your nuclei collide and overlap at some random offset at some impact parameter. And you can then flag the nucleons which are struck in the collision by some pairwise collision criteria. And then now if I just kind of artificially separate these two nuclei, I have all the participant nucleons in each nucleus, and I can construct what's called a participant density, which is a superposition of struck nucleon densities. So each nucleon is considered a source Gaussian, and you add up these Gaussians for all the nucleons which are struck. And now what you have is, realistically, you have those two participant densities which are overlapping, and that is, by some physics process, converted to entropy deposition. And so what you're looking for is some function or some mapping which converts local overlap density to entropy deposition. And that mapping represents a scalar function of two arguments. So its output is entropy deposition, and the two inputs are the local nuclear density in each nucleus. For this purpose, we proposed a generalized mean ansatz. So we said that the local entropy deposition was proportional to the generalized mean of the nuclear density in the colliding nuclei. The generalized mean is a function of one continuous parameter p. Ta and Tb are the local nuclear density in each colliding nucleus. And this parameter p takes values from negative infinity to infinity. As p goes to negative infinity, it becomes a minimum function. As it goes to positive infinity, it becomes a maximum function. And so it naturally interpolates between the two relevant scales of interest in the problem, which are the local minimum and maximum of the nuclear density at that point in the collision. And so for a specific value of p, it becomes some mapping. So for example, the simplest one is just p equal 1, which is an arithmetic mean. That's saying that your local entropy deposition is just the average of the local nuclear density. So on the left here, what I have is a cross-section. So this is one spatial coordinate, and this is nuclear density. I have a cross-section of a lead-lead collision. The gray band is the region spanned between the minimum and maximum of the local overlap density. And then this red line is the generalized mean of that configuration applied to the event. And so you see it interpolates somewhere between the two scales of interest. And then if I decrease p, I send it towards negative infinity, you increase the local attenuation of asymmetric entropy deposition. If I decrease p even more, you decrease that entropy deposition even further. So the really nice thing about this parameterization is that it does a very nice job recreating specific theory calculations in the literature. So we compared to 3 different theory calculations here. On the left, what I have is a figure of an individual event. So you have this mapping, which is some scalar field of 2 variables. And so you can take different cross-sections through that mapping. And then what we've done is we've tuned this parameter p in our model to recreate the mapping for these different theory calculations. So it's really remarkable. With one continuous parameter, we can have our model behave like other theory calculations in the literature, and that's why I refer to it as a meta-model. Now that we have our initial condition model, we want to embed it into a full Monte Carlo simulation. So we use this parametric TRENTo initial condition model. We use the latest and greatest hot QCD lattice equation of state. We use a second order relativistic viscous hydrodynamics code and parameterize intrinsic QGP medium properties such as the temperature dependence of the viscosity. And then finally, we use a hadronic afterburner to simulate collisions of the hadrons after particleization. Now, the challenge is we have this model and we have all these under-constrained parameters, and the model takes a long time to evaluate. So it's maybe 10 minutes to run the model once for one set of parameters for one event. And you really need, say, 10,000 events in order to evaluate a certain configuration of parameters. And so the challenge is you have all these parameters. You're in a very high-dimensional parameter space. If you change one parameter, you change different observables that you calculate from the model. So you're in a high-dimensional parameter space. It's very nonlinear. And if you just try to brute force it by running 5 parameter values for each parameter and just run the model for all those configurations, it would quickly become intractable without using a very large supercomputer. So the solution to this problem is to apply a modern Bayesian methodology, which is developed to constrain parameters for models which live in high-dimensional parameter spaces. If you've been following the LIGO experiment, you may have noticed that they use the same methodology to determine estimates for the mass of the black holes in the black hole merger. Essentially how this works is we have our physics model, and we evaluate our physics model on a certain number of training points. And these training points are just different parameter configurations which we run the model at. So we run it at 300 different parameter configurations which fill our 8-dimensional parameter space. And then we train a Gaussian process emulator on the output of the model. And the Gaussian process emulator is a non-parametric interpolation algorithm, and it acts as a fast surrogate for the true physics model and lets us evaluate the output of the physics model at some arbitrary set of input parameters essentially instantly without any computational cost. Once we've trained the emulator, you perform a Markov chain Monte Carlo. So you do a random walk through your 8-dimensional parameter space, and the walk update is weighted by the Bayesian posterior likelihood that your model is describing the experimental data. And so after many steps, this Markov chain Monte Carlo equilibrates to the posterior distribution, which is the probability distribution for the true values of the model parameters. So this is just quickly to show kind of the before and after. So this top row is 3 different experimental observables calculated from the model compared to experimental data, which are the black symbols. You see all these different lines. These are the 300 different model calculations using the training data. So you have a large spread in the model, and that reflects that the large initial range that we chose for the input parameters. After we've run the Bayesian analysis, we can then sample parameter values from the Bayesian posterior distribution. And now you see that the model is tightly clustered around the data. And the small spread that you see in the model reflects the true uncertainty in the model parameters. So this is actually what you get. This is what you're after. So you have this very large grid. The diagonal elements on this grid are the posterior distribution for a single model parameter where you've marginalized or integrated out the values of the other model parameters. And the off-diagonal elements are the joint distribution for 2 model parameters. And there's a lot of information in here. I don't have time to talk about all of it, but I just want to highlight a few key results. So we had this parametric initial condition model. We had this entropy deposition parameter, P, which was the generalized mean. And we get a very beautiful, tightly peaked distribution on this parameter. And I showed that you can tune this parameter P to mimic different theory calculations in the literature. And we can now show kind of unequivocally that we can support certain theory calculations, and we can demonstrate tension with other theory calculations, and we can do this quantitatively where we've accounted for all sources of uncertainty. I also talked about there's a lot of interest in determining the temperature dependence of the QGP viscosity. So this gray region is the original range that we sampled for the temperature dependence of the viscosity. It's according to this linear parameterization. And then the blue band is a 90% credible interval determined by the Bayesian analysis. And so this is actually the first credible interval for the temperature dependence of the QGP viscosity with quantitative uncertainty, and is a significant progress in our field. And what's really fascinating is there's actually a lower bound that's been postulated from string theory that the specific shear viscosity of a fluid cannot go below 1/4 pi. And it's actually pretty impressive that our calculation within the uncertainty is in agreement with this, this lower bound. Finally, now that you have the Bayesian posterior, you can take high likely model parameters from the Bayesian posterior. So you sample the peaks of the distributions, and you can run the model at those points and just say, how well does our model do? Because if you optimize a bad model, you're still going to get bad results. And what's really amazing is that we can simultaneously describe 3 different experimental observables to the 10% level or better for most of the parameters. And this is unprecedented. It hasn't been done before. These 3 observables are the particle yields. This is the average momenta. And these flow cumulants are just generalizations of this elliptic flow parameter for higher harmonics. So you have elliptic flow and triangular flow and quadrangular flow. And we've looked at all of these. And centrality here is a measure of you essentially take your events, you run minimum bias events, and then you can histogram them by the total multiplicity in the event, and you divide them into what they call centrality classes. So a 0 to 10% centrality class is a very central collision that produced a lot of particles. And so we get a very nice agreement with the data. And also, we also looked at particle production for different collision systems. So this was all done for lead-lead collisions. We can look at different collision systems at different beam energies, and we still get a very beautiful agreement between experiment and theory. So my conclusions, the physics conclusions are that in my summer project, we studied the Lattice QCD equation of state. We found that the current discrepancy between different lattice calculations is relatively small and doesn't lead to a significant contribution of error when you're extracting medium properties. We developed a new parametric initial condition model called TRENTo, which lets us, it's a meta model which lets us analyze a large space of different theory calculations within a single model. When we applied a Bayesian analysis using this parametric initial condition model, we found that local entropy deposition in nuclear collision is roughly the geometric mean, or the square root of the product of the nuclear density in the collision. And that this mapping agrees nicely with at least 2 state-of-the-art theory calculations. And we also published a first quantitative credibility interval on the temperature dependence of the QGP shear viscosity. And with that, I'd just like to thank Krell for the exceptional opportunity. It's been a pleasure being part of this fellowship for 4 years, and thank you.